welcome to the Deep Dive. Today we're plunging into a topic that's not just making headlines, but really reshaping industries and how we interact with information. Large language models.
LLMs.
Or LLMs. Our mission in this deep dive is basically to cut through the noise. We want to extract the most important facts, maybe some surprising insights, from a whole collection of sources.
Right. We've got academic surveys, industry reports, even expert guides on, how these things are evaluated.
The goal is a concise but still thorough understanding.
Exactly. We're going to trace the evolution, look at what they can actually do in the real world.
Practical stuff.
Yeah, practical stuff, but also confront the big challenges they still face, and then finally sort of demystify how we measure their performance and what's coming next.
And trust me, you'll hear some genuinely surprising facts, like how these incredibly smart abilities seem to just, emerge.
Almost out of nowhere, yeah, once they hit a certain size.
And why figuring out if they're actually good is way more complex than you might think. It's not just a simple test.
Yeah.
So let's dig into this.
Okay.
To really get a handle on what LLMs are today, we kind of need to quickly look back.
Set the stage, yeah.
Humanity's fascination with machine language intelligence, it goes way back. The 1950s, Alan Turing's famous test.
Right, the Turing test. That really sparked decades of research into how machines could, understand and generate human language.
Foundational stuff.
Absolutely. And that research, it's seen some pretty remarkable transformations over the years. Back in the 1990s, we had statistical language models.
Okay.
These were mainly about predicting the next word based on probability. Useful for very specific tasks, maybe basic search, speech recognition, but pretty rigid.
Limited.
Very limited. Then a big leap happened around 2013. That brought us neural language models.
Oh, neural nets.
Exactly. And this was a game changer because they introduced the idea of representing words not just as separate units, but as numerical embeddings.
Embeddings.
Wow. These captured their meaning, their relationships to other words. Think word2vec if you've heard of that.
Right.
This allowed models to understand words in context and learn features that weren't just tied to one single task. Task-agnostic features.
So a word wasn't just a word anymore. It had this kind of digital fingerprint of its meaning.
Yeah.
In relation to other words.
That's a great way to put it, a digital fingerprint. And the next monumental shift came around 2018 with pre-trained language models, or PLMs.
Okay, PLMs. This is where we start hearing familiar names.
Definitely. Elmo, BERT, the early GPT models, GPT-1, GPT-2, they used a revolutionary architecture called the transformer.
The transformer. Still key today, right?
Absolutely fundamental. And they were trained on just massive amounts of text data. The key idea was train a model on a huge corpus, first to learn deep language patterns.
Learn the language itself.
Yes, and then fine-tune it for specific downstream tasks. That made them incredibly versatile.
And that brings us to the pivotal moment, the real birth of what we now call large language models, LLMs, around 2020. We're talking PLMs, yes, but of a truly significant size. I mean, tens, even hundreds of billions of parameters.
Huge scale.
GPT-3 burst onto the scene, 175 billion parameters. Pollen went even bigger, 540 billion. The main survey we looked at uses 10 billion parameters as its baseline for large.
Yeah, it's a fuzzy line, but that's a reasonable threshold.
But here's the really mind-bending part. When the parameter count crosses a certain threshold, suddenly these LLMs show special abilities.
Emergent abilities.
Emergent abilities, things that just weren't there in the smaller versions, like in-context learning.
Exactly, where they learn from just a few examples you give them in the prompt. No extra training needed.
Wow.
And these emergent abilities, they're defined quite precisely as abilities that are not present in small models but arise in large models.
Okay.
What's so striking is how performance changes. It doesn't just get gradually better. It hits a certain point, a kind of critical mass, and then boom, performance on a task just skyrockets, way above random chance.
So it's not a smooth curve, it's a jump.
A massive jump. Think of it like a phase transition in physics. Water doesn't slowly freeze, right? At 0 degrees Celsius, it suddenly turns to ice.
Okay, I see the analogy.
Or like in human language development. A child doesn't just get incrementally better at sentences. There's a leap from single words to making basic sentences.
Right.
Now, there's some debate. Some suggest maybe this sharpness is partly how we evaluate tasks, the metrics we use.
Oh, okay.
But for you, the end user, the perception is definitely discontinuous. I mean, a piece of code the model writes either works or it doesn't. There's often no real in between.
That makes sense. The practical effect is sudden, and the real-world impact of these milestones, like ChatGPT's release, was huge.
Undeniable.
Academic research just exploded. The number of related papers jumped from, like, less than half a paper per day on average
Right.
to over 8.5 papers per day.
It's an incredible acceleration. Just shows the intense interest in the pace of innovation. And that explosion, it translates directly into this massive leap in what we call task-solving capacity.
Yeah.
LLMs aren't just modeling language anymore. They've effectively become general-purpose task solvers. Think GPT-4.
Right.
This hugely broadens their scope and just supercharges their performance across an amazing range of things language models can now tackle.
So now that we've traced that incredible journey, how they evolved, let's shift focus. What can they actually do?
Yeah, the practical applications.
Because it feels like they're starting to transform how we interact with tech every single day.
The applications are incredibly diverse. I mean, take text generation. LLMs are like digital scribes.
Scribes, yeah.
They can complete sentences, draft really detailed product documentation, even create, short children's stories like Alexa Create does with personalized tales.
Okay. What about coding? I hear a lot about that.
Oh, code generation is a huge one.
Yeah.
They're remarkably proficient. You've got models like Amazon Code Whisperer, OpenAI's Codex, which powers GitHub Copilot.
Right. Copilot.
They can generate code from just natural language prompts in Python, JavaScript, Ruby, you name it. Or even generate SQL queries, shell commands, website designs.
So for developers, it must be like having this super fast coding partner right there.
Exactly, a very capable assistant. And in conversational AI, think about Alexa, Google Assistant, Siri.
Our virtual assistants.
LLMs are making them dramatically better, much better at understanding your intent, handling complex, nuanced commands. Beyond that, we're seeing LLMs modernize whole industries. Newsrooms are using them for content generation. They're being used for privacy tasks like anonymizing data.
Wow.
The impact is rippling through the whole AI community. In NLP, natural language processing, they're now the go-to general purpose solvers. It's shifted research paradigms.
Right.
In information retrieval, search engines, well, traditional search is facing real challenges from AI chatbots like New Bing.
True.
Even in computer vision, image processing, there's a huge push to develop ChatGPT-like vision language models. Multimodal dialogue. GPT-4 can already handle image inputs alongside text.
It really sounds like LLMs are becoming the sort of central brain behind a lot of the digital tools we use.
That's a good way to think about it.
So what does this actually mean for you, the listener?
Well, it suggests we're really on the verge of this potentially prosperous ecosystem of real-world applications.
Okay.
Think about products like Microsoft 365 Copilot, powered by LLMs, aiming to automate chunks of office work.
Freeing people up for other things.
Oh, yes, for higher-level tasks. And look at ChatGPT supporting plugins now. That lets it connect to external tools, extending its reach into specialized functions.
Right, like booking flights or ordering groceries.
Exactly. It's really pointing towards a fundamental change in how we interact with technology, making it more intuitive, more powerful, more seamlessly integrated into our lives.
It almost feels like magic sometimes, doesn't it?
It can feel that way.
But behind that magic, there's this immense amount of technical skill, engineering muscle.
Oh, absolutely. Years of work.
So let's try and pull back the curtain a bit. How are these incredible systems actually built from the ground up?
Okay. Well, it all starts with data, and its role is just foundational, absolutely crucial.
Dated.
LLMs demand a truly astronomical amount of training data. We're talking hundreds of billions, maybe even trillions of tokens.
Tokens being like words or parts of words.
Exactly. Individual words or subwords. And this data has to be incredibly diverse. You need web pages, like from Common Crawl.
The whole internet, basically.
Pretty much. Entire libraries of books, Book Corpus, Project Gutenberg, Wikipedia, of course, mountains of code from GitHub, Stack Overflow, academic papers from ArcStreet, even conversational text from places like Reddit or Open Assistant.
So you're basically feeding them the entire digital library of humanity, more or less.
In essence, yes. But, and this is key, it's not just about throwing everything in. Data preprocessing is critical.
Cleaning it up.
Massively important. It's this painstaking process of cleaning out the noise, the duplicates, the irrelevant stuff, and especially the potentially toxic data. You do this through really rigorous quality filtering, toxic filtering, deduplication. Imagine sifting the entire internet to find only the cleanest, most useful parts.
Sounds like a huge job.
It is. Then comes tokenization. That's how the raw text gets broken down into those individual tokens the model actually understands.
The subwords and words.
Yep. Subword tokenizers like byte pair encoding, BPE, are really common because they handle new words or complex terms pretty efficiently.
Okay.
But you have to be careful. Issues can pop up, especially with non-English languages or even with numbers. You can get inconsistent splits.
And that matters.
It can subtly impact things like the model's numerical ability or even just how fast it responds, the inference latency.
Wow, so a tiny error in breaking down a word early on could cause a ripple effect down the line.
Precisely. And finally, within data, there's data scheduling. This is almost an art form.
Scheduling, what does that mean?
It involves two things. One is the optimal data mixture, the exact proportions of different sources you feed the model, like Llama's pre-training data. Over 80% web pages. And the other is the data curriculum. That's the order you present the data during training. Maybe start with simpler stuff, build basic skills, then move to more complex concepts, like teaching a child.
That's incredible. So much careful curation and planning, even before the model technically starts learning anything.
Absolutely. It sets the foundation. Then we move to the blueprints, the model architectures.
Right, the transformers we mentioned.
The transformer architecture has really become the standard for LLMs. It scales well, it's effective. But even within that family, there are important variations.
Okay.
The causal decoder is hugely popular. That's the backbone of the GPT series models. It's essential for their in-context learning because it's designed to predict the next word based only on the words that came before.
Looking forwards, not backwards.
Exactly. There are also encoder-decoder architectures like FLAN-T5 and prefix decoders like GLM130B, different ways to structure the processing.
So it's not just about making them bigger, but there are these fundamental differences in how they're structured to kind of think about sequences of words.
That's a great way to put it, yeah, how they process sequences. And then the huge challenge, training and inference efficiency.
Making it actually feasible to build and run these things.
Right. Training LLMs is computationally enormous. Just imagine needing hundreds, sometimes thousands, of powerful GPUs working together perfectly.
Wow.
Techniques like 3D parallelism, splitting the workload across the data, the model's internal tensors, and the training pipeline are essential. Bloom, for instance, needed 384 top-end A100 GPUs just to train.
Incredible compute power.
And managing the memory is a nightmare. So they use methods like zero and offloading parts of the model or the calculations to the regular CPU memory.
So it's like designing this incredibly complex superhighway system just for data, just to keep these massive models fed and learning efficiently.
It really is a constant optimization challenge. And a really significant innovation used in GPT-4 is predictable scaling.
Predictable scaling.
Yeah, it allows researchers to accurately estimate how well a massive, super expensive model will perform based on training much smaller, cheaper versions first.
Ah, so you don't waste months and millions training a dud.
Exactly. It drastically reduces development time and cost, lets you know if you're on the right track early on.
Sure.
And once it's trained, you need it to respond fast, right? For inference. Flash attention is a clever algorithm that optimizes memory use during the attention calculations.
Making it faster.
Much faster, reduces memory bottlenecks. And speculative decoding is another cool trick.
Speculative.
It uses a smaller, faster draft model to generate potential next tokens, and then the main big LLM just quickly verifies them.
Like having a quick assistant do the first pass.
Precisely. That can give you like 2-3x speedups, makes the interaction feel much more instant.
It sounds like this constant race for efficiency, squeezing every bit of performance out, even after the main training is done.
It's an ongoing engineering marvel, truly. And then there's how these models actually generate the text, token by token, the decoding strategies.
How they pick the next word.
Right. The simplest is greedy search. Just picks the single most probable next token. But that can lead to really repetitive, kind of boring output.
Okay.
So that's where sampling-based methods come in. They introduce a controlled element of randomness, diversity.
Make it more creative.
Potentially, yeah. You use techniques like temperature. High temperature means more randomness, more surprise. Low temperature means more focused, predictable output.
Like a dial for creativity.
Kind of. There's also top case sampling, where it only samples from the most likely next tokens, and top sampling, which samples from the smallest set of tokens whose probabilities add up to p.
Different ways to control the randomness.
Exactly. And models often tailor these strategies, like Llama might use greedy search for straightforward question answering, but use sampling for more creative tasks like code generation.
So it's like that detective analogy again. Predicting the next word in a novel, but sometimes the detective needs to be strictly logical, other times a bit more imaginative, depending on the case. The model's understanding helps it choose.
That analogy holds up really well, and the refinement doesn't stop after pre-training. LLMs are constantly adapted. Prompt engineering is huge.
Crafting the right question or instruction.
Yeah, manually designing effective prompts is practically an art. It's super sensitive to wording, and a really well-designed prompt can massively boost performance on complex tasks. Then there's in-context learning, ICL, which we mentioned, learning from examples in the prompt. What's fascinating is that task recognition, just figuring out what task you want it to do from the examples, can happen in smaller models.
Okay.
But true task learning, actually acquiring new knowledge or skills from those demonstrations, that seems to only really emerge in the big LLMs, like 66 billion parameters or more.
Interesting distinction.
Yeah, and techniques like symbol tuning are being developed to help LLMs genuinely learn from demonstrations, not just match patterns they already knew.
Okay.
And maybe one of the most impactful techniques recently is chain of thought, Sainte prompting.
Chain of thought. I've heard that phrase.
It's often as simple as adding, let's think step by step to the prompt, or giving examples that explicitly show the intermediate reasoning steps.
And that helps.
Substantially. Especially for complex reasoning tasks, arithmetic, common sense questions, it really boosts performance. And amazingly, this reasoning ability seems to generalize. Like, training on math problems can improve its physics problem solving.
Wow, that's powerful.
And finally, LLMs can act as the core processing unit for LLM-based agents.
Agents. Like robots.
Not necessarily physical robots, more like intelligent software agents that can perceive digital environments, make decisions, plan actions, and execute them to achieve goals. They integrate memory, planning, the works.
So they're not just responding, they're acting based on the LLM's brain.
Exactly. It's a big step towards more autonomous AI.
It's really clear this whole development process is incredibly iterative. It's not just build it once. It's constant refinement, pushing the boundaries.
Absolutely. Continuous improvement.
So we've seen the amazing capabilities, the incredible engineering behind LLMs. But like any really powerful new technology, they come with significant challenges, right?
Right, definitely. It's not all smooth sailing.
Some of the biggest questions are still wide open. Let's dig into those hurdles and how researchers are trying to tackle them.
Sounds good. One of the really persistent issues is what you might call mysterious underlying principles.
We don't fully get why they work so well.
Pretty much. We still don't fully understand why those emergent abilities pop up or what the exact key factors are that make these huge models so capable. Plus, a lot of the crucial training details from the big industry labs are kept secret.
Trade secrets.
That's right, which makes it harder for the wider research community to fully investigate and replicate. It's a bit like having this amazing engine, but not quite having the full blueprints for how it works internally.
Okay, that makes sense. What else?
A huge one is alignment. Aligning the models with human values and preferences, because LLMs can generate toxic stuff, biased content, or just factually incorrect nonsense.
The harmful outputs problem.
Exactly. So how do we fix that? One method is red teaming.
Red teaming, like in cybersecurity.
Similar idea. You deliberately try to provoke the model into generating bad outputs using humans or even other AIs to find the vulnerabilities. Then you can work on patching them.
Okay.
A really cornerstone technique now is reinforcement learning from human feedback, RLHF.
RLHF, heard of that too.
Yeah, basically you train a separate reward model. Humans look at different outputs from the LLM and rank them which one is better, more helpful, less harmful.
Humans provide the preference data.
Right, and that reward model learns human preferences. Then you use that reward model to fine-tune the main LLM, guiding it towards better behavior. It's proven effective, like with Llama 2, in making models more helpful and harmless.
Interesting.
There's even RLAIF reinforcement learning from AI feedback.
Using AI to train AI.
Kind of. You use an already well-aligned LLM to generate the feedback instead of humans. It can massively speed things up and cut down on the human effort needed. And there are other approaches too, like constitutional AI or self-align. These actually get the LLM to critique and revise its own problematic responses based on a predefined set of ethical principles or rules of constitution.
So the model learns to police itself based on rules we give it. That's a fascinating feedback loop.
It really is a form of self-correction. But even with alignment efforts, we still grapple with hallucinations.
Right, when they just make stuff up but sound confident about it.
Exactly. Generating factually wrong, nonsensical, or maybe plausible sounding, but totally erroneous information.
How do you fight that?
It's tough. Ongoing alignment tuning helps. Integrating external tools like search engines or databases so the model can fetch real-time credible information.
Like the RJA idea we'll get to.
Precisely. And also giving models ways to estimate their own uncertainty. Maybe if it's unsure, it says so. For detection, researchers use models to spot hallucinations in other models' text, or look at uncertainty metrics like the probability of the tokens it generated. There are specific benchmarks too, like Truthful QA or Howley Weevil, just for measuring this.
Okay. What about reasoning? Are they always logical?
Not always. That's another tricky area. Reasoning inconsistency. Sometimes an LLM gets the right answer, but through totally flawed logic.
Oops.
Or the opposite, follows a perfect reasoning path, but somehow ends up with the wrong final answer.
Frustrating.
Very. So people are working on guiding the generation process with external tools or using iterative self-reflection. Techniques like self-refine or tree of thoughts let the model review and correct its own reasoning steps.
Thinking about its thinking.
Kinda, yeah. Process-based supervision helps too. And sometimes just reformulating a reasoning task as a code generation task can enforce more logical consistency.
Because code has to be logical.
Exactly. And one more practical challenge, numerical computation. LLMs still often struggle with math, especially big numbers or symbols they didn't see much during training.
They're language models, not calculators, right?
Fundamentally, yes. But we need them to handle numbers better. So solutions include fine-tuning on math problems, teaching them to write out intermediate steps like on a scratch pad.
Show their work.
Yeah. Integrating external tools, like actual calculators via plugins, helps too. And even the tokenization matters. Llama's tokenizer handles numbers better by avoiding weird splits, and that seems to boost its arithmetic ability.
It's really clear that even with all the progress, these challenges aren't just small bugs. They show LLMs are still very much an active research field. Lots more to figure out to make them consistently reliable.
Absolutely. It's evolving incredibly fast.
So given this complexity, both in capabilities and challenges, evaluating them must be really hard too.
Oh, hugely.
It raises that important question. How do we even know if they're good at what they do, beyond just having a quick chat with one?
That's a critical point, because the old ways, the traditional metrics, they often just don't cut it for LLMs.
Like what kind of metrics?
Statistical scores like BLU, Rouge, Meteor, Levenstein distance, they mostly measure word overlap. How many words in the model's answer match the reference answer?
Okay, seems simple enough.
But they completely fall apart when you need to evaluate actual reasoning or deep understanding. They don't get meaning. They're like judging a gourmet meal by just counting how many ingredients match the recipe without actually tasting it.
Right, they miss the point entirely for complex tasks.
Totally. Which is why researchers are increasingly leveraging LLMs themselves for evaluation, using LLMs as judges.
Using the AI to judge the AI.
In a structured way, yes. One method is the G-Evil algorithm. You use an LLM, maybe GVSci4, to first generate a series of evaluation steps based on criteria you define, like rate this answer 1 to 5 on coherence, then 1 to 5 on factual accuracy, using chain of thought.
Okay, create the rubric.
Exactly. Then you use an LLM, maybe the same one, to apply that rubric and output a score.
Seems a bit circular.
It can be, which is why another method, the KAG score question-answer generation, is gaining traction. It uses LLM's reasoning, but crucially avoids having them generate the final score directly.
How does that work?
First, you use an LLM to read the model's output and extract all the factual claims it makes.
Yeah.
Then, for each claim, the LLM formulates a simple, close-ended question, like a yes-no, I don't know question. Then, you check that question against the ground truths, or the original source document. Finally, you compute a mathematical score based on the results, like the percentage of truthful claims.
So the LLM helps break down the problem and formulate checks, but the final scoring is more objective, based on comparing to facts. That sounds more robust.
It generally is considered more reliable, yes. Of course, there are other LLM-based metrics too, like BERT score or mover score using embeddings, but they can sometimes have their own biases.
Okay. And what about for specific systems like RAG?
Yeah, for retrieval augmented generation, you need specific metrics. Like answer relevancy, does the answer actually address the user's query concisely? And contextual precision.
Contextual precision.
That measures how much of the generated answer can actually be traced back to the specific documents the system retrieved. It tells you how well the retriever did its job finding relevant stuff.
Makes sense. You want the answer based on the retrieved facts.
Exactly. Now, in terms of actual evaluation benchmarks and findings, there are tons of benchmarks out there. General ones like MMLU, Big Bench, and specific ones testing coding ability like Human Eval, hallucination like HalEval, medical knowledge like Multimed QA.
So what are the big takeaways from these evaluations?
A few key things stand out. One, closed source models like ChatGPT, Claude often perform really well as general purpose solvers, especially on the hard tasks. ChatGPT often showed superior performance compared to earlier models on things like complex math problems.
Okay. What about open source models?
Instruction-tuned open source models like Llama 2 Chat, Vicuna generally outperform their base, non-tuned versions on specific tasks. That instruction tuning really helps.
But maybe with a trade-off.
Sometimes, yeah. Maybe a slight dip in general language modeling ability, but a big gain in following instructions. However, the smaller open source models still tend to struggle significantly with really deep mathematical reasoning or tasks requiring interaction with an environment or using tools effectively.
Size still matters.
Size definitely seems to matter. Llama 2, even the smaller 7B version, showed surprisingly good overall performance, especially on complex reasoning. That's likely down to its huge pre-training dataset, around 2 trillion tokens, and really rigorous data cleaning.
Quality data again.
Always. And ultimately, the power of scaling is just consistently confirmed. Bigger models generally outperform smaller ones, especially as tasks get more complex, like symbolic reasoning or advanced math.
So this whole complex, evolving evaluation landscape is just crucial. It's how we actually track progress and ensure these models are becoming safer, more reliable, and genuinely useful, not just, impressive novelties.
Absolutely fundamental. You can't improve what you can't measure effectively.
Okay, as we start to wrap up this deep dive, let's pivot to the bleeding edge.
Where things are headed.
Yeah. If we connect all this, the evolution, the capabilities, the challenges, the evaluation, where are LLMs going next? What are the big frontiers?
Well, one of the most critical strategies right now is retrieval augmented generation, or RAG. We touched on it.
Right, helping with hallucinations and keeping info current.
Exactly. It's a powerful way to enable LLMs to access and incorporate external, up-to-date information. Think of it like giving the LLM a super fast research assistant that can pull in relevant facts on demand.
So it's not just relying on its sort of frozen internal knowledge from training. It can look things up.
Precisely. The basic workflow is, first, context retrieval. Find relevant info from outside sources, the web, documents, databases.
Okay.
Second, prompt construction. Intelligently weave those retrieved documents together with the user's original question or task.
Build the context.
Right. And third, response generation. The LLM uses that combined input, the prompt, plus the retrieved info to formulate its final answer.
And how are they improving RAG?
Lots of ways. Better retrieval, maybe using smaller propositions or ideas as retrieval units instead of whole documents for more precision. Using LLMs to rewrite queries to be more effective. Refining the results, re-ranking retrieved documents, filtering out irrelevant bits, even iterative retrieval where the model refines its search based on what it finds initially. Plus, specialized training to make LLMs better at using the retrieved content.
Sounds like a whole field in itself.
It really is. Another major area is long context modeling.
Handling more information at once.
Exactly. Extending the model's ability to process much, much longer input sequences. We're seeing models like GPT-4 Turbo handle 128,000 tokens. Claude 2.1 up to 200,000.
That's like a whole book's worth of text.
Easily. This needs clever tricks for how the model tracks word positions over long distances, called position embeddings. And it often requires extra pre-training, even if just a small amount, on carefully chosen long text data.
So they need specific training for long attention spans.
You could say that, yeah. And lastly, a really practical frontier is model compression.
Making them smaller.
Making them smaller and more efficient so they're easier to deploy. These models are huge, they take up tons of memory. Compression helps shrink that footprint.
How do you do that?
2 main ways. One is quantization. You map the high-precision floating point numbers the model uses internally down to lower bit integers like int8 or even int4.
Reducing the precision of the numbers, doesn't it hurt performance?
Surprisingly, often not much, especially with int8 weight quantization. And interestingly, really large LLMs sometimes seem less sensitive to this low-bit quantization than smaller models were.
Huh. Counterintuitive.
A bit, yeah. The other technique is pruning. This means literally removing parts of the model connections, parameters that seem less important.
Trimming the fat.
Exactly. You can do structured pruning, removing whole components, or unstructured, removing individual weights. The goal is to significantly reduce size while keeping performance largely intact.
So RG for better knowledge, long context for bigger inputs, and compression for efficiency. That paints a picture of more capable and more practical LLMs.
That's the direction, definitely.
So LLMs aren't just tools anymore. They're becoming these powerful, adaptable assistants. We're seeing them change scientific research, helping with literature reviews, hypothesis generation, data analysis, even writing paper drafts.
Big impact there.
And in vital areas like healthcare potential for medical advice, mental health analysis, education too, personalized learning, automating assessments.
The potential is huge across so many domains.
Absolutely.
But it's crucial to remember, despite all this incredible progress, those fundamental challenges we talked about, ensuring factual accuracy, tackling biases, maintaining user privacy, data security, they remain top priorities for ongoing research.
Right. We need to be careful and responsible.
But the sheer pace of evolution we're seeing really points to a profound revolution in how we develop AI and ultimately how we interact with it in almost every part of our lives.
So we've covered a lot today. We've explored this remarkable journey of language models, right from the theoretical origins, Turing's questions, all the way to these incredibly sophisticated general-purpose LLMs we have now. We peeled back the layers on those surprising emergent abilities.
Yeah, it's set and jump.
Glimpsed the complex engineering behind them, tried to demystify the clever ways we evaluate their performance, and looked at exciting frontiers like RAs and long context.
And the core message, I think, is that LLMs are really more than just bigger versions of older models. They seem to represent a fundamental paradigm shift in AI.
A qualitative difference.
Exactly. Demonstrating abilities we didn't really foresee. And the field is just so dynamic. New techniques, new applications are popping up constantly. It really invites continuous learning and exploration.
Which brings us to a final thought for you, the listener. As these large language models keep evolving at this incredible pace, becoming more capable, more integrated into our daily lives, how might your own understanding of intelligence, both human intelligence and artificial intelligence, shift or expand?
That's a deep question.
What new possibilities does this open up? And maybe just as importantly, what new responsibilities might this future demand from us as humans interacting with these increasingly sophisticated systems? Something to think about. Thank you for joining this deep dive.
Thanks for listening.